A new frontier in space exploration, NASA. This is just groundbreaking. NASA has contributed significant advancements in space technology, but this time, a time machine? Yes, you can say that. After the huge success of the Hubble telescope, NASA deployed a technological marvel in space. The new James Webb Space Telescope has opened a new horizon in the field of space technology. The main attraction is that it can really reveal the mystery of Big Bang by capturing images from the past. Hey, don't get confused, I'll explain. In today's video, we'll be talking about a new frontier in space exploration by NASA. So all of your questions are going to be cleared. Stay tuned. Hey everyone, welcome to the Tech Universe. This is the place to introduce you to the marvels of the universe of technology. We provide you data and facts from the world of technology that are informative as well as exciting. So to never miss an update, subscribe to the channel and don't forget to press the bell icon. That being said, let's begin. The James Webb Space Telescope, NASA's next flagship infrared observatory, was successfully launched on December 25, 2021. In collaboration with ESA and CSA, JWST will be ready for science operations in the summer of 2022. When it has been deployed into orbit and the mirrors and equipment have been aligned and calibrated, it will open to the whole scientific community and will allow scientists to view galaxy development, star and planet formation, exoplanetary systems, and our very own solar system in ways never previously imaginable. Understanding the universe's beginnings in search of extraterrestrial life, these are the mission objectives of the James Webb Space Telescope, the long-awaited successor to the Hubble Space Telescope. NASA, in collaboration with the European Space Agency and the Canadian Space Agency, launched the Webb from French Guiana on Christmas Day. The telescope is now functioning properly at the L2 orbits, a location roughly 1 million kilometers from Earth. Sarah Seeger, a planetary scientist and astrophysicist at MIT, says, "The Webb represents the culmination of decades, if not centuries, of astronomy. We've been waiting for this for a very long time." The Webb is named after the man who commanded NASA in the decade preceding up to the moon landing, which is disputed. Its namesake, James Webb, was a government official during a time when it was federal policy to dismiss gay employees. While current NASA Administrator Bill Nelson has stated that the agency has discovered no evidence at this time that supports altering the name of the James Webb Telescope, a petition accusing Webb of involvement in a discriminatory policy that has garnered over 1,700 signatures. NASA expects JWST to cost $9.7 billion over 24 years, between 2003 and 2021. $8.8 billion were spent on spacecraft developments, with $861 million set aside to fund 5 years of operation. The lifetime cost to NASA, adjusted the inflation to 2020 USD, will be around $10.8 billion. Wondering about the cost? Now see its size. The JWST Sunshield measures approximately 22 meters by 12 meters. It's roughly half the size of a 737 plane. Even a tennis court is roughly the size of the Sunshield. The aperture of JWST is 6.5 meters in diameter. To keep the telescope cool, JWST will include a large sunshield. This is true for all space telescopes, but it is especially crucial for infrared telescopes like JWST, since warm objects emit a lot of infrared radiation. If the telescope isn't maintained cold, it runs the danger of blinding itself to the light of the object it's trying to examine. The telescope aperture, on the other hand, is the most significant improvement. This is the diameter of the hole at the telescope's end, or in the case of telescopes like these, the diameter of the mirror that collects the light. It's the black hole in the center of our eye that lets light in, similar to the pupil. The bigger the aperture, the more light the telescope can collect in a single pass, and hence the fainter the object it can view. Hubble's 2.4-meter aperture allows it to view things that are at least 60,000 times fainter than the naked eye, which is then greatly extended by using cameras to take long-exposure photographs. With a mirror almost 3 times the size of Hubble's, JWST will be able to view objects nearly 9 times more clear than Hubble, allowing us to look further into space. The telescope was launched on Europe's Ariane 5 rocket, which includes a payload fairing, or a nose cone, that is 5.4 meters in diameter, making it one of the largest in the world. JWST's 6.5-meter mirror, which is made up of 18 hexagonal pieces stacked in a honeycomb pattern, is still too narrow. For launch, 3 pieces on each side fold back to allow the telescope to fit. JWST's other components were also packed for launch, making it a contortionist spaceship. The telescope's secondary mirror is held in place by 3 struts that fold together. The tennis court-sized sunshade folds and rolls into a compact bundle that requires a multi-step unpacking process. The telescope's solar panels, an antenna, and radiators that shunt surplus heat into space are among the other deployable components. JWST must block off heat from both the sun and its own equipment to observe infrared light. A 5-layer sun shield is the first line of defense, keeping the telescope at -233 degrees Celsius. JWST's sun shield resembles the solar sail of the Planetary Society's light sail spacecraft at first appearance. The sun's rays will still press JWST, thus the spacecraft incorporates a reflective trim tab that deploys at variable angle to assist counteract the effects of solar radiation. JWST reached L2 and all of its instruments and equipment were deployed, and the real fun began. Its hexagonal reflectors, which are coated with a small coating of gold to let it see in the infrared, bounce light from distant objects. The light goes up to a secondary mirror, which concentrates it into a dinner plate-sized beam before returning it through a hole in the primary mirror's sensor. It is then further focused and delivered via 4 separate scientific instruments. The further away an object is, the longer it takes for its light to reach us. So when we gaze at a faraway galaxy, we are seeing what it looked like in the past. When you gaze at the moon, you see it exactly as it was 1 second ago. It's been 8 minutes since the sun warmed your face on a wonderful day. Through binoculars, the Andromeda Galaxy seems to be a smear of light, yet it is 2.5 million years older than it appears. JWST can observe galaxies that are up to 13.4 billion years old, which is only 400 million years after the Big Bang. Due to the expansion of the universe, galaxies at this distance are rapidly pushing away from us. The Doppler effect, which allows an ambulance siren to sound higher pitched as it approaches you and lower pitched as it passes you, causes their light to have a longer wavelength. Long wavelength light from objects generated much closer to the Big Bang is moved into the infrared. Beyond Hubble's capabilities in certain situations, JWSTs may be able to view things as far back as 100 million years after the Big Bang, aiding our understanding of cosmic genesis narrative. Following a succession of successful milestones for the James Webb Space Telescope, there's even more exciting JWST news. After completing their initial alignment and focus, the 18 little mirrors may now generate a single picture of a star. However, unfolding the origami pieces was only the first step. The 18 sub-mirrors had to be oriented so that they could work together as a single unit, directing their separate beams of light to the same location in the observatory's cameras. On the rear of each mirror are mechanisms that allow it to be tipped, tilted and pulled to ensure that it is focused and aligned. Simply pointing the telescope at a star and seeing what each mirror was doing was the initial stage in the mirror alignment procedure. The star, HD 84406, a sun-like star around 260 light-years away, was chosen by scientists and engineers. It possesses well-known infrared properties and the appropriate brightness. The original image revealed 18 hazy blobs of light, as predicted. Then each mirror was rotated to determine which image originated from which mirror. There are 3 sets of mirrors designated, A, B, and C, with each group numbered 1 to 6. Because of the extreme precision required, the next processes take a long time. When you go to the eye doctor for a vision test, they show you 2 somewhat fuzzy images and ask you to choose which one is better. You could need 4 to 5 trials to get the right prescription to concentrate your eyes. When you're on step 2 or 3, JWST has 7 processes, each with several tweaks, and it is now on step 5 of its own process. The final 2 will take roughly as long as the first 5 and will be finished in the coming months. We cannot keep our calm imagining what pictures this telescope can send, and how was the universe before Big Bang? What if this JWST reveals that we have neighbors in space? It's irresistible. Anyway, we are at the end of the video. Consider giving a like if you enjoyed the video, and don't forget to share and subscribe. We will see you again in the next one. Until then, peace.